Hi there. In this video, we're going to discuss exponential growth and decay. So the exponential growth function is this one highlighted here, n of t equals n naught e to the rt. You may have seen it before in other classes as a equals p e to the rt or y equals y naught e to the rt, but the one that is used in our book is this one with the n. And so n of t is the number or the amount at time t, and where n naught is the original amount or initial amount. Just as before, right? With money, usually A is the amount, P is the principal, and if you have the y equals y naught, y is the amount at time t, and y naught is the initial amount. So those are the same things, we're just using different variables, but that is the formula that our book uses. So the example that I'm going to do to illustrate exponential growth, we're going to look at, since we are doing online stuff due to COVID-19, I figure we would use some of that data. So back in March, before we had a handle on things, this was the COVID-19 growth prediction by one mathematician. There were lots of data out there, but this one was one of the predictions, and based on data that was given from the CDC, this mathematician saw that if no action was taken, so if you just let the virus go unwatched, so without any social distancing or any measures to stop it, so no action, if one person gets infected, then after 10 days, 2.5 people get infected, and after 60 days, it was 406. And notice that this represents exponential growth. It's growing very fast. And then what if you limit the exposure to the infected person? And so we're going to look at no action taken and 75% exposure reduction. So this is the big measures that were taken for social distancing. So let's look at what the exponential growth model will say for this data. Okay, so using our formula, we know that n of t is equal to n naught e to the kt. So our goal is to find what is n naught and what is k. So say I want to know, so the big question we may have is how long, so how much time until 1 million are infected in the US. So this is data from the US. I'm going to use a table to represent this, what we know. So we know that assuming at time 0, we have one person infected. And we know that after 10 days, it was 2.5 people. And then after 60 days, it says there were 406 infected. So this is with no action. So that means that this is the initial, right? At time 0, 1 is the initial, so patient 0. So which means that n sub 0 is 1, which makes our equation be n of t equal to 1 times e to the kt. So now we need to find k. So we're going to use the second value to find k. So n is 2.5, so I'm going to go over here and say, okay, 2.5 is equal to, I don't need to write the 1, e to the kt, well, t is 10, so it's going to be equal to k times 10. And now I want to solve for k. Why do I want to solve for k? Well, if I want to know how long until 1 million people are infected, notice that if I take my 1 million and say equals n naught e to the kt, I can't solve for t, right? How long is a measure of time, so we want the value of t, but I can't find t without knowing n naught and without knowing k. We already know n naught is 1, but that still doesn't help us, because I will have 1 million equals e to the kt. I need to know k. So thus we use the second value, or I could have used the third one to find k. So solve for k. So this is an exponential equation. So I have e to the 10k, and my variables in the exponent. So this is where we use our logarithms. So write it as a logarithm. This is an exponential base e, so we're going to use the natural log to rewrite it as a logarithm. So b then log base e, so be the natural log of 2.5 will be equal to then 10k, the exponent. And now I can solve for k. Divide both sides by 10 to get k. So the natural log of 2.5 divided by 10 is equal to k. And I'm just going to leave it like that because I don't want to lose any significant digits. If I change it to decimal, I risk by rounding that I may be off from my answer. So now let's go back to the equation. My equation was this one, and now I know the value of k. So therefore, I can say n of t is equal to e to the k. K is the natural log of 2.5 over 10t. So now that I have everything that I need, right, the k and the n naught, we can find anything we want. So we wanted to find how long until we have 1 million people infected. So let's go back to the question. So our question was how long until 1 million people are infected. So pay attention to how the question is presented, how long, so we're looking for time. 1 million are infected, that's the number. So that means that n is equal to 1 million, and we are looking for time. So in our equation, I'm going to say then 1 million is equal to e to the ln of 2.5 over 10 times t. So we're looking for t. Again, my t is stuck in the exponent, so how do we get rid of it being in the exponent? We change it to a logarithm. This is the log base e. So again, we're going to use the natural log. So I'm going to have the natural log of 1 million is equal to the exponent. So the ln of 2.5, the whole thing divided by 10 times t. And the goal is to solve for t, so multiply or divide both sides by ln of 2.5 over 10, but since that's a fraction, dividing by this fraction is the same thing as multiplying by the reciprocal. So I'm going to multiply both sides by 10 over ln of 2.5, 10 over ln 2.5. So here, these cancel, giving me with just t. So t equals, and then we do this again on our calculator. So 10 times the natural log of 1 million, so do that on your calculator, and then divide it by the natural log of 2.5. So when we do this, I got t is 150.776. So we can say that t is approximately 151, and this was in days, so 151 days. So COVID-19, leaving it to its own devices, no precautions taken, it will take 151 days to reach 1 million people. So 150 days is what? Approximately how many months? So on average, there are 30 days in a month, so you can do 151 divided by 30, and so that will be about 5 months. Oops, months. So from March, count 5 months from March, so that would mean that by August, we would have had 1 million people infected. But there were some precautions taken, and that did not happen. And so some social distance went into effect. And so let's look at the one with the 75% exposure reduction. So one person infected, and after 10 days, it goes to 0.625 infected. So what's that? 5/8. So let's look at the 75% exposure reduction. And we're still assuming exponential growth, so we're going to still assume n of t equals and not e to the RT or KT. So now we have a slightly different model, right? I have T and N. So at T equals 0, we're still assuming one person. After 10 days, now we're saying 0.625, so 5/8 of a person is infected. So we've reduced it quite a bit by doing social distancing. And so same thing, let's look for, so this is our initial, so that means N naught is equal to 1. So that means that the equation becomes 1 e to the RT of KT. I think before I used K. And so I have that. Now this point is going to help me find the K. So I'm going to say N, so 0.625 is equal to E to the T is 10. So to the 10 R. And solve for R. So if I wanted to ask the same question, how long under this model will it take to reach 1 million people? Hopefully it will be a very, very long time. And so again, this is my variable stuck in the exponent, so we need logarithms to bring it down. So use the definition of a logarithm to write this in logarithm form. The base is e, so I'm going to have the natural log of 0.625 is equal to 10r, right? So what I'm using here is the definition of the log, that we have log base a of a equals, of x equals y. This can be rewritten as a to the y equals x. So we have the base is e, so I have an exponential and I'm going to a logarithm. So the base is e, so it becomes log base e, which is the natural log of x, the thing that is equal to the 0.625 equals the exponent, 10r. So now solve for r, so divide both sides by 10, so I have the ln of 0.625 divided by 10 is equal to r. And now what I want you to do is usually we're going to leave our constant like this and put it in our function. So it'll be e to the constant ln of 0.625 over 10 times t, right? But I just want to see, what is this? Let's put in our calculator and see what this number is. So when you do the natural log of 0.625 and then divide that by 10, you're going to get that r is approximately negative 0.047. So now that I have a negative number for this constant, normally we wouldn't write it like this because we don't want to lose, in rounding, we don't want to lose significant digits with rounding. But notice that this is now negative, whereas before our k was positive. And so remember what that means in terms of an exponential. This k here, this is a positive number. And so that means exponential growth. So for this, we are experiencing exponential growth because the ln of 2.5 divided by 10 is 0.916. So this is approximately 0.0916. So this is a positive number, so that means exponential growth. And for this one, I get a negative for that constant. And so this is actually exponential decay, which when we talk about flattening the curve, that's what we mean. We changed it from exponential growth going up to exponential decay, to decreasing function. So something that looks like that. And so that's essentially what you want. So are we going to reach 1 million with this model? No, because this is decreasing. So you're never going to reach 1 million. So if you try to put 1 million in here for n of t, you're actually going to get the t is going to be a negative number. And time can't be negative, so that means that we have an exponential decay function here, which is usually what you want to see. Just to show you a graph from this, I got from the World of Meter, which you can go and look at data. So when you look at March over here, hopefully you're able to see it. Notice how from March 12th to March 25th, that's that data that it was increasing very rapidly. It was our exponential growth. And then social distancing went into effect and it kind of curved it. So that's the flattening the curve, right? So we switched it from exponential growth to somewhat of a decrease, decay. But we are entering now our third wave of this because I think, what is it called? The COVID fatigue, quarantine fatigue is kicking in. So that's when you see things spike back up in exponential growth. And then we're able to bring it back down. And now we're starting to spike back out again. So those increases do happen exponentially. And so as you hear people saying we're entering the third wave, this is what it means. It increases, decreases. And then the second wave, it decreased, and now we're going on an increase again. So it'd be interesting to look at the data from, say, September to October and see what the exponential growth is. Because notice at least it's not as rapid as it was here. There were less cases in March, but notice how rapidly it grew versus there are a lot more cases here, but it's not growing as rapidly. So it may not be able to be modeled actually by exponential growth. In the next video, I'm going to do an example of exponential decay with half-life.